Okay, so today we're going to be talking about sketching the derivative given the graph of our original function. Okay, so we're going to be looking at these f of x graphs, and I've given you the equation as well, but we're going to be looking at what does the derivative look like given what I'm given. So we're going to use how the derivative relates. So if the original function is increasing, the derivative is positive or above the x-axis. If the function is decreasing, that means the derivative is negative or below the x-axis. And where my original function has a maximum or minimum point, that's where my derivative has a 0. Okay, which goes along with the first derivative test itself. When we do the first derivative test, we find the zeros of the first derivative, and then we find where it was positive or negative. And that's telling me where my function is increasing, decreasing, or have a max or minimum. Okay, so let's look at the first one. We have this quadratic here. Now, if we look at this quadratic, we already know that if we take the derivative of a quadratic function, we end up with a linear function. That's how the derivative works. We subtract one from the power. So we know that our actual first derivative will be a linear function given that this one's a quadratic. So we start with our maximums or minimums. So I have a minimum right here on the quadratic, which means that translates to a 0 in my derivative. So wherever I find a maximum or minimum, that's where my zeros are going to be, where it hits the x-axis. Then let's look at this left side. My function here is decreasing. Okay? And since my function is decreasing, that means my derivative is on the negative side. On the other side, the function is increasing, so the derivative is on the positive side. So this is basically what my first derivative would kind of look like. Okay? And that's kind of what we're going to be doing. We're just getting a rough idea of what our first derivative will look like when we graph it compared to the original function. Now, the second one, we have a cubic function, which means, like I said before, if this is power 3, our derivative should be power 2. So again, we start off where we have our maximums and minimums, and those will translate to zeros in my derivative. Okay? So here, on the left side, my function starts by increasing to this point where this maximum is. On the left side, it is increasing up to this point, which means our first derivative there is positive. It's on the positive side. Then from my maximum to my minimum, my function is decreasing, which means my derivative is negative. Then on the right side of my minimum, my function is increasing again, which means my first derivative is positive. So my derivative should match my original function's picture. So this is my f prime of x. Okay? All right. Let's look at something like this. So basically, on this problem, we have this rational function. Okay? We do have a asymptote right here. Okay? Now, I do have right here a relative maximum, which is a 0 in my derivative, and right here I have a relative minimum, which is a 0 in my derivative. Okay. Now, neither the function nor its derivative are going to cross that. They both are going to have an asymptote there. Okay. But let's look. Right here, when I'm going up to this point, it's increasing, which means my derivative is positive. And then on this side, it's decreasing, which means my derivative is negative. So it's going to look something like that. On the other side, this right here to this minimum point is going down. It's decreasing, which means my derivative is negative on the negative side. And on the other side, it's increasing, which means it's on the positive side. It's going to look something like that. Okay. Now, same thing for this last one. I've got these asymptotes right here because it's the secant. Now, a lot of my students would get confused on this left side because this arrow makes it look like it's increasing here because this arrow is going up there. But the function itself is actually decreasing, which means this right here is going to look like this. It's going to be negative. Same thing on the other side. But this side, my function is increasing, which means I'm on the positive side. It's going to look like this. Okay? Now let's talk about this middle part. This middle part has a minimum, relative minimum, so my derivative has a 0 here. And on this side, you can see it is decreasing from here to this minimum, which means my function is negative. And on the other side, it's increasing, which means my derivative is positive. And if you think about it, secant is what we started with. The derivative of a secant is secant times tangent. And you can kind of see that tangent graph right there in that middle with that cubic style looking thing. And you can even see over on this side where this is the beginning of the next one. Okay? So basically all of this that we're doing relates back to this chart. Now I've thrown in the second derivative as well. Okay? This red box represents your first derivative rules. So when f of x is increasing, my derivative is positive. When it's decreasing, my derivative is negative. When there's a minimum or maximum, the derivative is 0. The second derivative is the derivative of the first derivative. So if you notice, right here, increasing, second derivative is positive. Decreasing, negative. Minimum or maximum, or 0 in our second derivative. But it also tells us stuff about our original function. It talks about concavity and points of inflection. Okay? So we'll talk about more of these when we get to the second derivative test. But all three of these relate to tell me everything I need to know about my original equation. If I go back to, say, the easy quadratic one that we just finished with up here, where the first one was cubic. The second one, the first derivative is quadratic. If we took the second derivative, which means we took the derivative of the derivative and sketched it. Again, we start with our minimums. That's our 0. And just like in the first example, when we take the derivative of a quadratic, we end up with a linear function. So the second derivative looks something like this. This point right here in my original is telling me where the concavity change. It's called a point of inflection. And you see how the original function opens down here? See how it cups like down, like this, here? But on this side, it's like a cup that's opening up. This point right here is where it changes from those two. And that'll become way more important later when we deal with the second derivative test.